Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on February 3, 2026, just 2 days ago. It introduces a training-free framework that reduces the memory footprint of long video generation by up to 7 times, all while keeping latency overhead under 4%. The paper is titled Quant VideoGen Auto-Regressive Long Video Generation via 2-Bit Key Value Cache Quantization. And as we'll see later, these efficiency gains allow massive video models to run on standard consumer hardware, which is a really exciting development for accessibility. Well, Figure 1 visually demonstrates this efficiency gain. On the left, for the Longcat video benchmark, the standard model in the top row consumes 34 gigabytes, while the proposed method in the bottom row uses only 5 gigabytes. This massive reduction preserves quality, unlike the Kivi baseline in the middle row, which degrades into noise. The right side shows similar results for the HY WorldPlay benchmark, where memory drops from 21 gigabytes to just 4 with the new method. Alright, Figure 2 digs deeper into the trade-off between memory and quality. Panel A on the left illustrates the core dilemma. The top row shows that keeping a full key value cache preserves detail, but eventually hits an out-of-memory wall. The middle row tries a sliding window to save space, but notice how the image quality degrades and darkens significantly over time. In contrast, the bottom row, using Quant VideoGen, maintains the scene's vibrancy without crashing. Then, the charts on the right, panels B and C, reveal the secret sauce. They show high cosine similarity between nearby tokens, indicating massive redundancy that the algorithm can exploit for compression. So, following up on that redundancy, Figure 3 breaks down the semantic-aware smoothing technique step by step. Panel A on the far left shows the original key cache, which appears noisy and irregular, making it hard to compress efficiently. Next, Panel B applies semantic grouping, which reorders the data to reveal vertical structures, though the values remain high. The crucial step is in Panel C. Here, the method subtracts the average value, or centroid, from each group. The heat map turns almost white because the remaining residuals are tiny. Finally, Panel D proves the impact. The orange histogram shows the data is now tightly packed around 0, unlike the wide teal curve of the original, making it perfect for 2-bit quantization. Okay, Figure 4 maps out exactly how this pipeline transforms the data. On the far left, Panel A starts with the raw key value cache, where the values are mixed and irregular, leading to a high quantization error of 100. Moving to the center in Panel B, the system uses k-means clustering to split these values into stable centroids and small residuals. The top arrow, labeled residual branch, represents the progressive residual quantization, which iterates this process to refine the residuals further. Finally, Panel D on the right shows the output. The data is compressed into simple scales and quantized values, which drops the error drastically to just 0.1. Now, Table 1 validates these design choices with hard numbers, comparing the new framework against several baselines. Focusing on the top section for the Longcat video benchmark at 2-bit precision, the data reveals a clear divide. Standard methods like Kivi and Quaro achieve compression ratios of about 6.4, but their quality suffers significantly, with signal-to-noise ratios hovering around 21. However, looking at the bottom 2 rows of this section, QVG Pro and QVG tell a different story. The standard QVG model pushes compression to nearly 7 times the highest tier, while maintaining a score of almost 29, proving it can save memory without sacrificing visual fidelity. Well, while Table 1 covered static metrics, Figure 5 demonstrates how these models behave over long durations. Panels A and B track image quality across 700 frames for the self-forcing model. In Panel A, under the aggressive 2-bit setting, standard methods like Kivi, shown in teal, plummet in quality after just 150 frames. In contrast, the yellow and purple lines for QVG and QVG Pro hug the top, tracking the uncompressed baseline almost perfectly. Then, Panel C investigates the design by showing the error reduction at each quantization stage. The tall first bar confirms that the initial pass captures the vast majority of the signal, meaning subsequent stages offer diminishing returns. Wrapping up, 2 takeaways stand out. Quant VideoGen effectively breaks the memory wall, reducing memory usage by 7 times without retraining. By compressing the key value cache, it enables massive models to run on consumer cards like the RTX 4090 while preserving quality. This significantly lowers the barrier for generating long videos and interactive world models. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.